All right, let's get right into it. Today we've got a fantastic scientific detective story for you. This one's got it all. A super bizarre material, a puzzle that stumped scientists for more than 20 years. And get this, a final twist that links two of nature's fundamental forces in a way nobody saw coming. So, where do we even start? Well, it all kicks off with a pretty simple question. What happens when magnets get, well, frustrated? And no, I don't mean they miss their morning coffee. We're talking about a really specific, really cool phenomenon in physics. And the answer? Oh, it is so much weirder and honestly more amazing than you'd probably guess. Okay, so meet our main character, the star of the show. It's a compound called Ca3CO2O6. Now just look at its structure. See those long chains running up and down? Those are one-dimensional chains of cobalt atoms. You can think of each one as a tiny, tiny magnetic wire. Now inside each individual chain, all the magnetic spins are playing nice. They all want to point in the same direction. That's ferromagnetism. But the real drama, the real problem, is what happens between those chains. So those chains are all packed together in a triangular grid. And here's where it gets messy. Each chain wants to be pointed the opposite way of its neighbors. It's the classic physics problem called geometrical frustration. The analogy on the slide is perfect. Imagine three enemies who have to sit at a triangular table. A and B sit down, fine. But where does C go? No matter what, C has to sit next to someone they hate. There's just no winning arrangement, no happy, stable state for the system to settle into. And it's that frustration that kicks off all the weirdness. And just to make our mystery even deeper, let's bring in a close relative, Ca3CoRH06. I mean, look at them. These two are basically structural twins. They've got the exact same frustrated triangular setup of magnetic chains. So you'd think they'd act pretty much the same, right? Well, you'd be wrong. They don't. And that very difference was the first major clue that told scientists something really, really strange was going on here. So, let's talk about the first big clue. It popped up from a really puzzling observation about heat. See, when scientists started looking at how these materials react to changes in temperature, they stumbled on a huge difference. And here it is, spelled out in a paper from way back in 2003. What the researchers found was this. When you cool down our main suspect, C3CO2O6, right as its magnets start to line up, it lets out this sudden burst of heat. They call it a specific heat peak. But its twin, C3CoRH06, nothing. It does nothing. One of them gives off this little puff of energy, and the other one is completely silent. The big question was, why? Just zero in on that column on the right. Our material, Ca3CO2O6, shows that very clear peak. It's like it's shouting to the world, hey, I'm becoming magnetic now. But its cousin? It undergoes its transition with a total whisper. You can barely tell it happened. This was the first real sign that, even though they look identical on the surface, these two materials were playing by totally different rules on a deep, deep quantum level. Okay, but the plot was just getting started. The next clue was even weirder. It showed up when the scientists decided to really put K3CO2O6 under the microscope and hit it with a magnetic field. And what they saw wasn't just a little unusual. It was completely bizarre. So, check out this graph. This shows you the material's total magnetism as you crank up an external magnetic field. Now, normally for any regular material, this line should be a nice smooth curve, a ramp. But look at this. It's not a ramp at all. It's a staircase. You've got these sharp, perfectly distinct, evenly spaced steps. What is going on? And this is the question that just drove scientists crazy for years. The material isn't getting more magnetic bit by bit, it's doing it in these sudden quantum jumps. Think about it like this. Imagine filling a glass with water. Normally, the water level rises smoothly, right? Well, this is like the water level instantly jumping from being a quarter full to half full to three-quarters full. Instantly. That kind of thing just does not happen in the world we live in classical physics. It shouldn't be possible. So, for years, the case went cold. People were stumped. And then, finally, a 2025 paper comes out, and a team of researchers had cracked it. The solution wasn't anywhere in classical physics. The answer, as it turns out, was 100% pure quantum mechanics. The whole thing came down to this really mind-bending idea called quantum tunneling of magnetization. Okay, so in our everyday world, right, if you have a ball and you want to get it over a hill, you have to push it all the way to the top. It needs enough energy to get over that peak. Simple. But in the quantum world, things are different. The ball can sometimes just poof, appear on the other side. It doesn't go over the hill, it tunnels through it. And that, it turns out, is exactly what the little magnetic bits inside this material were doing. And they didn't just guess. They had the smoking gun. They had tons of evidence. For one, they found that the material's magnetic response changed based on how fast they ramped up the magnetic field. They also saw that the timing of these magnetic changes followed a really specific pattern connected to temperature. All of this stuff, plus the staircase itself, these are all classic textbook fingerprints of quantum tunneling. Case closed. So the big question is, why is this happening here? And it all comes full circle, right back to that geometrical frustration we talked about. Because those magnetic chains are so frustrated they can't settle down, the frustration literally breaks them up. They snap into these tiny, isolated magnetic units. Some are just single ions, others are little pairs called dimers. And these little pieces are so small that they just stop playing by normal rules. They become quantum objects and start following the weird, wild rules of quantum mechanics. Okay, so let's put all the pieces together. Step 1. Frustration breaks the magnetic chains into these little quantum bits. Step 2. We apply an external magnetic field, which basically builds an energy hill that these bits would need to climb over to flip their magnetic direction. But here's the thing. They don't climb it. Instead, when the magnetic field hits a very specific resonant number, say 1.2 Tesla, all the single ions tunnel through the hill at the exact same time. Boom. That's your first step on the staircase. Then you keep cranking the field up to 2.4 Tesla, and now it's the dimer's turn to tunnel. Boom, there's your second step. And just like that, the mystery of the quantum staircase was finally solved. But wait, this story isn't over. Not by a long shot. Because in solving this magnetic mystery, the scientists accidentally stumbled onto something even bigger, even more profound. They thought, hey, just for kicks, let's measure the material's electrical properties while we're doing this. And what they found was the final, stunning twist in the story. They discovered something they named the resonant quantum magneto-electromagnetic effect. I know, it's a total mouthful, but the idea behind it is just incredible. What it means is that every time those magnetic bits did their quantum tunneling thing, it was directly and instantly triggering a change in the material's electrical properties. And here's the money quote, right from the researchers. They basically say that the jumps they saw in the electrical properties were happening at the exact same magnetic fields as the jumps from the quantum tunneling. The evidence was just staring them in the face. It was unmistakable. And this right here is the big aha moment, the final piece of the puzzle that locks it all in place. What you're looking at here are graphs showing the rate of change for both magnetism and electricity. That black line, that's the jump in magnetism. The blue line, that's the jump in the electrical property. I mean, just look at it. The peaks, those sharp spikes, they line up perfectly. Every single time the magnetism takes a quantum leap, the electricity takes a leap right along with it, at the exact same nanosecond. I mean, it's a beautiful and incredibly profound result. It's not just that one thing is affecting the other. It's so much deeper than that. They are literally locked together, dancing to the exact same quantum beat. A change in one is a change in the other, and the whole dance is choreographed by the bizarre rules of quantum mechanics. So why should you care about any of this? Well, discovering a brand new way to link magnetism and electricity at the quantum level, that's huge. I mean, this could be the key to unlocking new kinds of quantum computers or ways to store information that are way more dense than anything we have now, or even tiny electronics called spintronics. This isn't just a weird science curiosity. It's a fundamental discovery that could plant the seeds for the tech of the future. And that leaves us with one last really exciting thought. This entire incredible quantum dance, it was hiding in plain sight inside a material that scientists have known about and studied for decades. And it was all uncovered because of something as simple as frustration. It really makes you wonder, doesn't it? What other amazing, strange, and powerful secrets are just sitting out there, hidden in the world of materials, waiting for someone to come along and ask the right questions?